In this video, I'm going to continue my series on the Beaglebone by demonstrating how to use its GPIOs for both input and output. In previous videos I introduced the Beaglebone and demonstrated how you can use the board, and I followed this by a video on how to program it using Eclipse with a cross-platform C/C++ compiler. In this video I'll wire up simple input and output circuits that are attached to two random GPIOs. GPIO stands for General Purpose Input-Output, and the Beaglebone has 4 banks of 32 GPIOs, some of which are already allocated, for example to the onboard LEDs. Only 66 GPIOs are accessible from the 2 expansion headers. This is because the pins on the Beaglebone are multiplexed, meaning that one of the outputs of the P9 or P8 headers can have several different modes. I'll demonstrate how we can switch between these modes. Very importantly, these are 3.3 volt pins, and unlike a board like the Arduino, they should only source or sink a very small current. From what I've read, this is about 4 milliamps. All of the GPIOs can be configured as inputs or outputs, which I will also do in this video. The eventual aim of this video is to demonstrate what looks like a very simple circuit, but is actually surprisingly complex. I want to write a C/C++ application that when I press a button, an LED toggles, going on if it's off or off if it's on. The button will be connected as an input and the LED as an output. I'm also taking care that I drive a very small current through the GPIOs using a transistor to switch the LED in this example. To do this I have to deal with polling, which I will cover at the end of the video. This is the final circuit that I've wired. You can see here that over here I've got my output side. This is where I'm going to light, turn on and off an LED using the GPIO pin. Over here I've got my input side using a different GPIO. I'm going to read values into that GPIO using a momentary push button. So on the output side you can see that I've wired up a transistor to ensure that the currents are kept low through the GPIO pin itself. And the way that I've wired that is as in the previous diagram. I've connected this here, this red line is running into pin 7 of my Beaglebone, which is my sys 5 volt supply. This comes from the USB power, whereas for example there's another pin here, pin 5, which is VDD 5 volts, but that is only connected when the 5 volt barrel jack is connected, and since we're using USB to power this circuit we have to use pin 7. So that's connected to the positive side of the LED through the resistor, and this runs into the collector of the transistor. The base of the transistor is connected via a 10k ohm resistor to the pin 12 on the Beaglebone, which is GPIO 128. That's the marking that's down for that. And then finally the emitter of the transistor is connected via the black wire to ground, and this is my ground rail, which is connected to pin 45 of the Beaglebone, which is a general ground. So that's the wiring of this circuit here. This circuit ensures that when the current is applied, when a very small current is received from pin 12 of my Beaglebone, that this causes and triggers the transistor to turn on, in which case we have a current that flows from the collector to the emitter of the transistor, lighting up the LED using this 100 ohm resistor to drive the current through the LED. So that's the circuit for the output side. On the input side I have a momentary push button, and here I have it in pull down configuration. So this is normally connected, so it's normally connected low, and you can see this because the yellow wire here is connected to pin 25 of my Beaglebone, which is GPIO 3_21. So that's my my input. That's where I'm going to read the value from. That's connected via this 10k resistor to ground, and that means that when the switch is normally open, that this particular pin is grounded through the 10k resistor to ground, so it's normally a value of 0. And when you press the button, you can see that we've also got this orange wire which is connected to the other side of the button. So when you close the button, it means that we're causing this pin to go high. Now very importantly, this orange wire is connected into pin 3 of my Beaglebone, which is VDD 3V3EXP. This is a 3.3 volt supply. We would damage the board if you were to connect this to 5 volts, as the GPIOs have an upper limit at 3.3 volts. So just be careful that if you have got a high line that you're driving it from the 3.3 volt supply. So that's the circuit as wired. Again, we use the same ground here. This is connected to pin 45 of the Beaglebone, and that's my ground. The first part of the circuit that I'm going to look at is the LED output that's connected to my pin 12 on my P9 header. So what I've done here is I've connected to my Beaglebone by secure shelling into 192.168.1.109, which is my Beaglebone, and I've logged in as Ubuntu. I have a Ubuntu installation on this particular Beaglebone. So pin 12 on my Beaglebone on P9 header, the first thing we've got to do is work out what it is exactly. Well, if we go to our manual, and this is the Beaglebone manual, we see that pin 12, here we go, you can see that this is GPIO 1_28 in mode 0, so this is what we're going to look at. It's GPMC BE1N, I assume that's a mistake, it should be BEN1, and you can see that mode 1, 2, 3. Now we want to use it as a general purpose input output, so we want to use it as GPIO 128, so it means that we're going to have to change the mode of this. So if we go down, we can see that, well, pin 12, if we look at this, we can see that we have to get it into mode 7. So mode 7 on pin 12 is when it's GPIO 128. Now each one of these GPIOs is in a bank of 32. So GPIO 0 has 32 GPIOs, GPIO 1 has 32 GPIOs, and so does 2 and 3. So it means that the actual pin that we want to access, or the actual GPIO that we want to access, means that we have to multiply whatever the current bank is by 32 and then add in our particular pin. So in this case we're on number 12, so that's GPIO 1, means we multiply 1 by 32 plus 28, that gives us a value of 60. So GPIO 60 is GPIO 128. Okay, I hope that makes sense. So the first thing we've got to do now is to set up this pin to behave correctly. So it's GPIO 128 on pin 12, and the mode 0 again on mode 12 is GPMC BEN1. Okay, I think that's a typo. That should be definitely BEN1. Okay, so what I'm going to do is I'm going to go to this location where I can set up this pin. The first thing I'm going to have to do though is I'm going to go into super user mode. So I'm going to have to sudo sh just to be given access to allow me to set the values in my syskernel directory. So the way that we set this up is go to syskernel and debug, and you'll see here we've got my OMAP, where is it? OMAP mux. Okay, I'm doing ls. And here you can see these are all the mode zeros of all the pins on the P9 and P8 header. So somewhere in here we must have GPMC BEN1. So there it is. Okay, so it's GPMC BEN1. So this is mapped to pin 12 on the P9 header that we've connected our LED to. Okay, so let's just cat that. GPMC BEN1. Okay, so we can see that these are the signals on that particular pin. So there's seven options if you like. 0 is GPMC BEN1, 1 is this, 2 is not available, 3, 4, 5, 6, and finally 7 is GPIO 1_28. And you can see at the moment it's actually OMAP mux mode 7, so it's actually in the correct we're lucky it's actually in the correct format. If it wasn't, we can simply set the mode. So we could change the mode, for example, by setting echo 0 to GPMC BEN1 and then cat GPMC BEN1. You can see that I've changed it to OMAP mux mode 0. So that allows us to switch which particular mode that we're looking for. So I'm going to set it up again for GPIO 128. So we can do it by typing echo 7 to GPMC, where is it gone? BEN1. Okay, and then you can see now I've set it up for mode 7. So that means that it's set up as GPIO 128. Now we'll look at exactly what this 7 means here and this value means here. We'll look at it in the context of the input button rather than dealing with it in the output. So we'll leave it at that for the moment. So GPMCBEN1. So now we've set up the pin. The next thing we need to do now is to export the pin. So we can do this by going to /sys/class. Okay. And in here you can see we've got our GPIO. So we can do cd GPIO and ls. So you can see that currently I have no pins GPIOs exported. You can see these are my 4 banks, 0, 32, 64, 96. So the one we want again, GPIO 128. So that's 32 plus 28 is 60. So we need to export GPIO pin 60. So the way we do this is we can just simply echo 60. Now I'm in super user mode, root mode, to export. And now when we do an ls, we see that we now have a GPIO 60 appear. So we can go into that directory now, 60, and we can go ls. There's L, and you can see that we've got different values that we can set. This is sysfs, so this is mapped to the physical devices, like a file system, but it's mapped to the physical devices. And here you can see that we've got our, well, the ones we're concerned with here are direction and our value. Let's check the current direction. So we can say cat direction, and this is input. So we need to change that to be output. So we can go echo out to direction. So now we've set this up as an output pin. My LED is currently off. And we can set the value. So at the moment, if we want to turn the LED on, we can simply go echo 1 to value. And my LED comes on. I can echo 0 to value, and my LED goes off. So it's working correctly as it stands. And that's the LED part. So that allows me now, and I'm going to show you how to write a C++ program about C++ program about that, but that's the LED part working now. So the second part of this particular circuit is the switch. So I've used pin 25 on the P9 header. So let's get our documentation out again. And I've just picked 2 random pins. I didn't put any time into picking these pins, so I probably picked bad pins if we were to use other headers and so on, but it's just as an example. So again, it's pin 25 on the P9 header. So if we look at this, I'm mode 03. Oh, I have picked an awkward one. If you see pin 25, it's GPIO 321, that's what we want. And it's the mode 0 name is MSASP0_AHCLKX. Okay. Lovely. We'll have to find that. But you'll see if we go down to mode 7, which is on page 56 of the Beaglebone manual. Now that I know that can change. This is just the P9 MUX option modes 4 to 7. So modes 4 to 7, again we're on pin 25. So you'll see that if we go to mode 7, it's GPIO 321. So 321 means that we have to multiply 3 times 32 plus 21. 3 times 32 is 96, plus 21 is 117. So this is GPIO 117. Okay. But first of all, we've got to set up this particular pin to be in mode 7. So if we go back again with 25, you see we're looking for MCASP0AHCLKX. I'll just leave that to the side so I can find it. Okay, so let me just stick that. So we need to go to that directory. So again, back to sys kernel debug and the OMAP MUX, and it's here somewhere. MCASP0. I think that's it, is it? MCASP0 AHCLKX. Okay, that's the one there. So I need to change the mode now. Well, let's just echo that first of all. Echo MCASP0 underscore AHCLKX. Oh, lovely. Oh no, cat that. MCASP0 MCASP0 underscore AHCLKX. There we go. Okay. Oh, it's set for mode 7 as well. Now I was messing with it. I don't think that, well, we'll see anyway. MCASP is set to OMAP MUX mode 7. So you can see there 0, 1, 2, 3, 4, 5, 6, 7 is GPIO 33_21. And it's in mode 7, and it actually is 0027. Now, this 0027 is important. That's a hexadecimal value. Okay, the 0 by, it's a hexadecimal value, so 27. So we could write 27 is, well, let's just write it's two pairs, 0010, 0111. That's what 27 looks like. And that maps to a certain set of values. Now let's see if I can find it over here. This is on page 973 of the detailed description of the Beaglebone. And there's a table there. It's table 9.3.1.50. And you can see here it says conf_module_pin register offset 800. And you can see here that I might try and get a zoom in of this. You can see here that these are the bits that we're setting. So the last 3 bits down here, let's try and center that, are the pad values. So this is our mode. So 111 will be 7, so that's the mode. So they're bits 2 to 0 are the bits that we need to set. So 111 is 7. If we use a 0 for the third bit, that says we're using pull up, pull down, enabled. So that's enabled, that's what that pin means. So we're probably always going to have a 0 there if we're setting things up. And then we'll see that we want to set up pad pull up down type. Well, if we want pull up or pull down, in this case, we'll set it for 0 for pull down selected. And then finally, I suppose this is the one that sets us up as an input or an output. Input enable value for the pad, 0 for disabled, 1 for enabled. So we want 1. We want to use this pin as an input pin. So this means that the 5th bit needs to be a 1. So we're going to go for, and this one here, faster or slower slew rate. I'm not too sure what this means, but at the moment 0 fast sounds good, so we'll use that. So 0, 1, 0, 0, 1, 1, 1. Okay, and let's look at, is that what I have? Well, that's what I have here, 0, 0, 1, 0, 0, 1, 1, 1. So that's 2, 7, 27. So we can echo, or echo, oops, echo 27, it's hexadecimal, to MCASP 0 AHCLKX. And just to show you again that this is working, MCASP 0 AHCLKX. Okay, so that means that that pin is set up now as an input pin. It's in OMAP MUX mode 7, and you can see that the flag here 0 by 027 means that it's an input pin. If you don't set this, you simply won't be able to read values in on this particular pin. Okay, so now we go back to the same setup as we did for the LED. We can go into sys class ls, and we can go into GPIO ls, and we need to export the pin. So we need to echo, and its pin, again, it's 321. So 3 times 32 is 96 plus 21 is 117. So we echo 117 to my export ls. And you see that we now have another virtual GPIO 117. So we can go into this directory, GPIO 117. We cat the direction. Oh, it's an in. Well, okay, echo in, it doesn't matter, it's set for in, so it's an input direction, so it means we should be able to read the value in. And then we simply go cat value. So cat value is 0. Let's do it again. Is 0. Cat value, and this is the all important one. I'm going to press the button, so I'm holding my finger on the button, and my button, I'm holding the button down. Cat value, we get a 1. I've let go of the button, and we're back to 0. So you can see here that this allows us to read the value of a button. Now, it's not perfect because obviously you have to hold the button for as long as you need to, so that you can enter in cat value and enter return. Otherwise, you'd have to poll it at a high speed in order to find the change or transition. So that's how we would do this through sysfs through the command line. I think that's important before we move on to the C++ example, because you have to understand the architecture before we start to do it through C++. One other thing we can do is we can go into /sys kernel, debug, And we can do this. We can say cat GPIO. And if we do that, this shows us our particular values. And this is quite useful too, because here you can see there's our 117 and it's set up sysfs. That's the one for the button. You can see it's an input pin and it's currently low. And also, what was the other one we set up? It was, what was it? It was pin GPIO 28, so it was pin 60. So here's our 60, and you can see that GPIO 60 is connected to, it's an output pin and it's currently high. Yeah, the LED's on the board. And there's our 4 user LEDs, 53, 54, 55 and 56 and 35. I'm not sure what 35 is. So you can see here that there are pins. If I press the button, for example, well, let's just get this GPIO so I can do it with one hand. Press the button and you can see currently this is low. If I press the button, you can see that it switches my input to high. So by catting GPIO in this directory, we can see the values at a glance across all our GPIO pins. So I think that's a useful little additional feature that's available. In a previous video I showed you how to set up Eclipse for cross-development to the ARM platform. So there's a video that I'll put a link to here that shows you how to set up the Eclipse environment. So after you've watched that video, you'll have a good idea about what I'm doing here and how I'm cross-compiling to my Beaglebone platform. But here what I'm doing is I'm just going to write a very simple application, and I'm going to make it simple, and I'm going to avoid setting up different functions, and really I should do that. For best practice I should be setting up a different function to export a GPIO pin, to read a value and so on. So just to keep it simple and to make it easier to explain, I've just written it in a single function. But as I said, you should, if you're building on this, you should build it into different functions. So what I've done here is I've just created a single C file called hello-world-test.cpp, C++ file. And I've got my IO stream, just my standard input output. I've got my C stdio.h and my string.header file. So this just is my standard includes. I'm using namespace standard like I did in C++, just so I don't have to explicitly name the namespace every time. Hash define max 64. I'm just setting an upper length on the path length at 64 characters. That's to some degree arbitrary in this example. So here's my two functions, my flash GPIO LED and my read button functions. And these are just function prototypes that I've obviously written them down here. Int, in this case, I'm not returning a value that's on use. It's just an exit condition to say whether there was success or failure. So the first one, flash GPIO LED, is what I'm going to concentrate on first. So you'll see here, I'll just comment out this function here, read button. So my flash GPIO LED takes the GPIO pin, which in this case is 60, and the number of times that we want to flash the LED. So I'll just save this so I remember. So here's the function. It says flash GPIO. We pass in the GPIO pin and the number of times. I just print out a message to say, just to give me a status update at the command line, just to give me an just to let me know that the application function started. I have my handle, my file handle, which I've called LED handle, and then I've got these strings, and these strings are simply, I want to have it so that I pass in the pin. I don't want to hard code in the pin number. I want to be able to change it from GPIO pin 60 to 61. So I just take this int that comes in here and I turn it into a little string. So if 60 comes in here as an int, we need to convert that into a 60 string. So to do that, I'm just string printing this value %d to the string buffer, which case we now have a string with the value 60 in it. I then use that as well. I also do the same for the path to the value and the path to the direction. So this will be sys class GPIO 60/direction. And this just means that we can change this pin without having to change the strings that are here. So the first thing we do, just like we did the shell, was to export the pin. So we open up fopen sys class GPIO export, and we use it for a pending binary. We write in a pending binary format, and then if we can't create that file handle, we print out an error message. If we can open the file handle, we pass in the GPIO string, which is the number 60, which means that we've essentially exported the GPIO 60. We close the handle when we're finished with it. And I'm just going to keep reusing this handle, and now I'm opening the direction. So GPIO direction refers to this this string here, sysclass GPIO 60/direction, and we open this up for read write in binary format. If we're not able to do that, we print out the message. The direction says whether it's an input or output pin, so in this case we want it to be an output pin, so we copy out into our set value and we send the set value, F-write that to the output stream. So it means then that we set that this is an output pin. The next part is just to flash the LED however many times. So in this case it's 5 times. I multiply this by 2 because, well, 5 times I'm just going to iterate between on, off. So for 5 blinks of the LED you need 5 ons and 5s off. So that's going to be 10 times. So I do the same thing. I open up the handle. I open it up for read-write access, for binary write access. If I succeed, I continue on. And I just have a simple test here. imod2. And imod2 simply says modulo is the remainder after division. So 10 mod 2 would be, it would go in 5 times with a remainder of 0. 9 mod 2 would go in 4 times with a remainder of 1. So this is a very simple little check here to look for every second number is either even or odd. So for example, 9 mod 2 would be equal to 1. So on an odd value, we turn off the LED. On an even value, we turn on the LED. We write that value. And finally, when we're finished with the handle, we close down this file handle, and we have to do that at each loop. And that's something with this sysfs that's a little bit strange, is that you have to close the handle every time you want to send a value, otherwise it won't be sent. Finally, we can unexport the pin, which means that we're now removing the GPIO pin. It's not exported any longer, so we unexport this in the same way as we created the export. And finally, we print out our message. So at the moment here, I've set this up. Flash GPIO LED, 60 is the GPIO pin. We want to flash it 5 times. So saved, it's saved. So project, build all. So it's building away, and you can see here its success. You can see it's using the ARM, Linux, GNU, EABI, G++, the same as the last video. So we ended up with our ARM executable here in our project directory, and I'm just going to copy this and paste it into my remote server. Again, that was covered in the last video. So paste it in here. Okay, overwrite it, and now I can open my shell. So just move that here, and you can see that where am I? Exit. Just make sure I'm CD. Exit. CD. Okay, so I'm in my home directory, so it's in the hello world test directory. So here's my executable, and if I try to execute like this, well, it's not going to work. /hello world test. It's going to say cannot export the GPIO pin, and that's because at the moment I'm logged in. Who am I? I'm logged in as Ubuntu, and I need to run this as root for it to have access to the GPIOs. So here I can say sudo /hello world test, and there we go. So yeah, it's working. I can see on my board the LED is lighting, going on and off, and it has done it for 5 times. Okay, so that's my application running, and you can see one other thing that you can see here is that if we go into our sys class GPIO and we do ls-al, you can see that there are no exported. In this case 60, it was GPIO 60 would have been exported under the previous example. The unexport has happened as well, so the 60 has bin removed from the list as well. So there are no exported pins at the end of this function run. I can do the same again for, I'm just going to put myself back into that directory, so it'll be there when I get there. I can do the same then, so let me, in this case here, I'm going to call the read button function and turn off this flash GPIO LED, and save this, and project build it. Check that it works. Okay, all working. But I'm just going to show you the code. It's essentially the same piece of code. Now this isn't good coding practice to essentially cut and paste code, and really this needs to be wrapped up into separate functions, but it's fine for the moment, just for the example. So in this case here, I take the input pin, and I think as in our previous example, that was 117 as our GPIO. So with this pin here, I open up, print out the pin, and I do the same thing again, except for obviously instead of 60 being pasted in here for %D, 117 is going in. I export the pin 117, okay, and that's fine. I set the direction of the pin. I do the exact same with the exception that instead of out, we now want an input pin. So in is the value that we write to the direction handle. Finally, our button handle, we want to read in the value of the pin. So we can go RB plus, we set up a file open on the same handle, on the value handle. But instead of F write, we're using an F read. So we read in the value at the button handle, and then we're going to print this out on the console, on the shell. So we get our value and we display it. And finally, we unexport the button, the GPIO again for the button. So you can see here, because I've repeated the code, it is possible to create a function called unexport, and that will be a lot neater to do. But again, just to keep it simple. So that's saved and built. I think I built it, didn't I? I did, yeah. So I can go into my project and I'll copy my executable again. You can automate this task as well, but I just haven't done it for the moment, so I don't confuse myself. Overwrite. Okay, so bring up the shell again. So the application this time, I've used the same application. You can see that the time will have updated on it, and we can go sudo dot slash hello world test. So you can see the value that was read in is 0, 0, 0, and it's not going to change. So I'll put my finger on the button. So I've pressed the button and I go do the same thing again. So now fingers on the button and you can see that it's reading in a value. I've let go of the button and you can see we're back to reading in a value of 0. So that's an example of just reading the state of an output pin. It's not perfect because at the moment it's just simply reading whether the switch is pressed or not pressed. It's often the case that for things like a keyboard press, we need to be able to decide exactly when it happens. So for example, if someone presses the button at the moment, it has no effect. It's only reading the value at the exact instant when this program runs. So we need a way of either polling or using interrupts to read a value in from a button so that we can almost pause until a button has been pressed. This is the final source code example, and it's the most complicated source code example. In the previous case, we could check at a particular point in time if the button was pressed or if the button was not pressed. The problem is that that's not good enough in our applications. We need to do something, generate an event or work out when a button is actually, the very instant that a button is pressed, we might want to do something, or when a sensor is activated. So to do this, we're going to use, in this case, the poll function. And the poll function allows us to watch for events on a number of file descriptors. So the file descriptors are the handles that we use, for example, when we linked to the LED or the GPIOs themselves. We were able to open up a file descriptor and we're able to watch those using poll. So here's the final source code that I'm using, and I haven't written this myself. This is the example from the Ridge1 Run website. It's called GPIO int-test.c, and it's from Ridge1 Developer Connection, and I'll link that to this here. And this example here is a polling example, so it uses the poll.h header file. And as well as that, it neatly ties up, like what I was saying in the previous example. It would be nice if we could tie up into individual functions each one of the different calls we had to the file system, and this would mean that we could reuse them for example, instead of repeating the code for the LED and the button, we could use the same code over again. So in this case here, it links our sysfs GPIO directory to sysclass GPIO. We have a poll timeout of 3000 milliseconds, which is 3 seconds, and we use a max buff of 64, which is again the same for our path that we used before. So the first function, and you'll see it looks very similar to what we had to do, was to export a GPIO. We had to, you remember, we had to echo the GPIO number to /sys/class/GPIO/export. And effectively that's what's going on here. Sys/class GPIO is pasted in here, /export. And we're opening that and we're writing, in this case, we're writing the pin number directly to that export value. And this means that we're able to write to that. And that means that if successful, we get our GPIO pin exported. So that has nicely wrapped up that export function. And they've written it the same for unexport. It's the same thing. It just obviously to unexport, write to unexport instead of export. We can set the directory. direction. If we want an input direction or an output direction, we can set the value. So write to the value field of the sysfs. That would be to write a 1 or a 0 to turn on or off the LED, or to read from the value. We have a get value. In the case of the button, we might want to read in the value from that. So this is very nicely packaged up. One that I didn't talk about was set edge. And set edge decides if we want a rising edge or a falling edge detection on an input. So in the case of the button example earlier, you will notice that there was an edge direction flag that we could, or value that we could set, and we could either set it as rising or falling. So that's available to us too. And we also have open to open the particular value and leave that. This allows us to create an open file descriptor. So rather than sort of opening, doing something and closing, we're opening and then we're waiting and we're holding that descriptor, and then we're able to then close it later on using this function. And that's very important for polling. We need to be able to hold that file descriptor open, otherwise we can't check for events occurring on it. Okay, here's the main function, and the main function is where I suppose it gets slightly more complicated. What we want to use is this poll function. Where is it? It's down here. The poll function requires this FD set, the number of file descriptors, and a timeout. Now the timeout is very simply 3000 milliseconds or 3 seconds. The NFDS in this case is 2, and that's because we're going to check for events occurring both on the keyboard, which is our standard input, and also on our GPIO pin, in this case our pin 117. So what does the poll function do? Well, it provides applications with a mechanism for multiplexing input-output over a set of file descriptors such as these two here. For every member of the array pointed to by this descriptor, the function examines the file descriptor for the events specified in the events field. So this, in this case, would be high priority data that we may be read without blocking in the case of our interrupt or our poll to our button. And in the case of our keyboard, it's just poll in. It's data other than high priority data. And we've just specified that there. You can look at the documentation on poll within the man page of poll to find out there's a set of different event types that you can check for. So these are linked to the file descriptors. So GPIO FD is a file descriptor associated with this high priority data check that we want to do on this particular file descriptor. And this comes from here. This comes from when we open the file descriptor. And you remember I said that there's an open and a close. Well, at this point here, GPIO F_FD is the file descriptor that we get when we call that open function and pass it, in our case, 117. So we have an open file descriptor on our button input into our GPIO associated with our button, in this case obviously 117. So when we set this up, the poll function identifies the file descriptors on which an application can read and write data, or on which certain events have occurred. So it identifies if an event has occurred on one of these file descriptors. So we can say, and we do a check here, and we see that there's, in this case, we have 4 possible outcomes. We have the situation where the response, the RC, which is an int, it returns back a value. And the RC in this case, if it returns a negative value, it means that it's been unsuccessful in polling. So it means that something has gone wrong and we can quit out the application. If it returns back a 0, it means that the call timed out and we loop again. So it means we've met our 3000 milliseconds and we can loop around again. In this case here, if the response is fd set 1.reverts, which is a sort of ANDed set of tags and poll priority. So we're saying if it's this fd set 1 that reverted and it's a high priority event, it means that the button has been pressed, and then everything that we do here is related to the press of the particular button. If, for example, it was fd set 0 reverts, which is the keyboard input from the terminal, and poll in, which is our data other than high priority data, well, in this case here, we read the value and then we can print it to the console. We flush the standard output and we loop around forever until we, for example, hit Control-C in our application. So what happens here? Well, let's look at the, well, let me see, what else did I skip? Well, we'll come back to this in a second. The other thing that we have to do here before this, we use memset, and memset simply takes our FD set and writes zeros into the size of FD set. So it just clears the block of memory. Is there anything else I haven't described? Just go through them. There's our data structure for our sets of file descriptors and events. We've 2 file descriptors open at the one time. We have our buffer, which is just our character buffer. Our ints for our GPIO and our LED. This is simply 60 for LED and 117 for GPIO. They're the values we pass from the, well, I'm going to pass them in, so where do I get them? Here we go. GPIO is going to be the value, so we read in from the command line. If the number of arguments is less than 3, well, we're using it incorrectly, so we have to pass in the pin number and the LED pin. So we would execute this by typing GPIO -int 117 comma or space 60, and this would be the 2 values. So we read them in A to I, convert these into ints, and then we export these to the GPIO and the LED. We set the direction of the GPIO, which is the button, to be an input, the LED to be an output. We set the edge direction on the GPIO for the button to be rising, so that we're looking for the rising edge in the button. And then, as I said, we open this file descriptor for the GPIO for the button. So we don't close it here. We don't do anything once we've opened it. It's held open until we close it down here. GPIO FD close. So if we quit out of this, which actually it's not very well written, it's a while 1. So at the moment, we're probably not calling that directly. So let's look at the final part is, let's look at the situation where the button is actually pressed. Well, we read in our FD set. We need to read this buffer and clear it, otherwise we're just going to get events triggered over and over again. We print out a message on the console to say that GPIO %D, so we're just reading that from up here. We have no other way of identifying it at the moment, as an interrupt has occurred. If toggle LED, so this is a true or false value, so if the LED is on, we set the LED to be off, otherwise we set the LED to be on, and then we just invert this value or negate this negate this value. So if it's true, it becomes false. If it's false, it becomes true. That means that every time that the button is pressed, it means that we loop through this, and it means that the LED toggles from on to off to off to on. So we can see that working if I execute it here. Just project build all. Okay, there's a few warnings, and they came with the code. The warnings are very simple, and perhaps you can tie this up yourself. You see len is here and it's not being used, so there's a few warnings there. So we'll take that, it built correctly, so copy and then paste it to our remote server. Paste and overwrite what's there. Okay, and then we'll go into our directory, or we're in the right directory. So we need to execute this as sudo /hello world test, and then the 2 pins. So the button is connected to pin 117, GPIO 117, and the LED is connected to pin 60, I think. Okay, I need my password. Okay, so interrupt occurred. So let's just see what happens. So you can see the dot appears, and the dot appears every time we if you remember, if the where is it gone to? It's down the bottom. Every time we revert, so we've 3-second timeout, and every time this happens, we just print a dot to the console just to explain that it's still alive. So you can see here that the dot appears every 3 seconds. So if I press the button on the board, we see that an interrupt has occurred. The LED has come on. If I press it again, an interrupt has occurred, the LED has gone off. And so it works like that. Every time I press it, an interrupt has occurred on GPIO 117, and the LED goes on or off. Okay. If I type something, you can see that at the keyboard and press enter, you can see that we're getting values in. I assume they're let me just see. There are values we're getting in from our console. So it means that we're not only are we checking for events on the button directly, we're also checking for events on the standard input stream. So that example shows how you can tie a button to an LED and how you can trigger an event to occur when a button is pressed. It's complicated enough, surprisingly complex for such an application, but I suppose that it shows you that it can be much more than a button. It can be an event that occurs at any time, or it can be something much more complex in your application. Okay, so just to show you the actual circuit working, you can see here we've got our push button as before, we've got our LED circuit as before. I'm very simply driving it now. The application is running on the Beaglebone. It's checking for events to occur on my button, which is pin 11 is GPIO 117. And when I press the button, very simply the LED comes on. Press it again, the LED goes off. So every time I press it, we're triggering an event, and it doesn't matter how long you wait between presses. It's working correctly, and it's polling for the duration for however long you wait between button presses. So while yes, it's a simple application and it gives a useful output, you can see that we're linking to the input on one GPIO is affecting the output on another GPIO, and I think that's a useful example that can be used for many applications.